So last class we looked at a comparison of two models. One where we said the true average house price is dictated by both the size of the house, but also whether the house has a garage. And we did that by including this garage indicator variable. So this indicator variable was 1 if the house has a garage, and 0 if there is no garage present. And so remember, this garage variable is not counting the number of garages, but it's just saying is a garage present on the lot or not. And so when we did this, we were able to fit the model using a prediction equation. And so this blue line was a prediction equation y hat equals a plus b 1x1 plus b2x2. And this represented when x2 equals 0, that is, when there is no garage. The red line represented the equation, the prediction equation. The red line represented the prediction equation y hat equals a plus b1x1 plus b2x2 when x2 equals 1, that is, there is a garage. So again, not counting the number of garages, just saying, indicating if there is a garage when x2 equals 1, and there is no garage when x2 equals 0. So this prediction equation, when there is a garage, becomes y hat equals a plus b1x1 plus b2. And down here, this blue line becomes y hat equals a plus b1x1. And then because x2 equals 0, that whole last term goes away. So we can see that the equation treats the model for house price with homes with and without garages as constant. That is, the average change in price for a 1-unit increase in house size for homes with a garage is the same as the average change in price for a 1-unit increase in house size for homes without a garage. So this here, the average change in price for 1-unit increase in house size, this is B1. And the average change in price for a 1-unit increase in house size, this is also B1. So we have that same slope for any fixed value of whether there is a garage or not. And that is that same multiple regression interpretation. So when x2 is held constant, the average change in house size, or the average change in price when house size increases by 1 is B1. And that is true when we have a garage and when we don't have a garage. And then we looked at, well, does this make sense? Is this constant relationship reasonable? So here I've created best fit lines. So this is best fit lines for homes with a garage and without. So this is y hat when x2 equals 1, and this is y hat when x2 equals 0. So the blue line is still representing homes without garages. The red line is still representing homes with garages. But now we can see that the relationship, this difference, is no longer constant. Or we can see that when we have a home with a garage, the slope is different than the homes without garages. Right? So if we just look at the best fit lines, we're going to get a different relationship between house size and price depending on the level of x2. And that here gives us evidence of an interaction. So for two explanatory variables, or two predictor variables, or two different x terms, an interaction exists when the effect of one variable, so the effect of one predictor on the response changes with the level of the other predictor. So let's see. So the effect of house size on price is the slope. So the effect, this is slope. So here we have a relatively weak effect. So we have a relatively shallow slope when x2 equals 0 for homes that do not have a garage. So for one level of x2, for one level of homes with for the garage variable, we have a relatively weak effect or low effect. So there's a small gain in price due to increases in house size when there are no garages. For the other level of the garage variable, we see a much bigger effect. So over the same change in house size, we see a much bigger gain in price at that other level of the garage variable. So that is a change in the effect of size for a change in the level of the other variable, x2. We can see it the other way, right? So if we change levels of size, so here, holding size constant at 6,000 square feet, we have a very big difference in the average cost of a house between those that have garages and those that don't. However, for homes that have 2,000 square feet right here, there's no difference in the cost of a house between those that have garages and those that don't. So that is, again, seeing a very different effect of the variable garage and no garage, just changing the level or changing the size of a house. So that means that we have an interaction present. So this means that the lines on the plot are not parallel. So how would we reflect this in our model? So in our model, we have to get different slopes somehow, or we have to be able to change the difference in the effect of having a garage or not, depending on the change in the house size. So our model, it's going to start off the same. We're still going to have mu equals alpha plus beta 1 x1 plus beta 2 x2. And if we were to leave it as that, we're still going to have those parallel lines, because this is what we're forcing it to do. We're saying that when there's a garage, we have the same slope, and when there's no garage, we have the same slope, because this is that multiple regression equation. So this beta 1 is saying for a fixed level of x2, we're going to have that same constant change x1, beta 1, as x1 increases by 1. So we have to do something that's going to take into account the changing levels, or how those x1 and x2 variables interact. So we're going to call this beta 1, 2 to account for the interaction between variables x1 and x2, and that's going to be just by multiplying our variables x1 and x2. So this here, this is called an interaction term. And this beta 1, 2, this is an interaction effect. So without this last term, beta 1 would just be the simple effect of x1 on the response. Beta 2 is the simple effect of x2 on the response. But now, if I let x1 and x2 vary together, I can see a change in the effect of x1 or x2 when the other one changes. So let's see what that looks like. Well, when the house has a garage, that means x2 equals 1. So my model becomes mu equals alpha plus beta 1 x1 plus beta 2 times 1 plus beta 1, 2 times x1 times 1. So now I still have that same constant, so this is going to lift or lower my intercept just as before. But now I can see that I have an additional change on that slope. So let's group our terms together. So I've got alpha plus beta 2, so that's my intercept, plus beta 1 plus beta 1, 2, x1. So here I've just pulled my coefficients on x1 together. So now I can see that when I have a garage, my slope changes by beta 1, 2. Beta 1, 2 is the change in the slope, or the effect of size, is the true change of house on the price for homes with a garage. So how different is the slope when a house has a garage than houses that don't have a garage? So versus homes without. So let's see how that really compares. So when the house does not have a garage, that means x2 equals 0. So starting off with our same model, mu equals alpha plus beta 1 x1 plus beta 2 x2 plus, get that interaction term in there, beta 1, 2, oops, let's do this again, beta 2 x2 equals 0, so we'll just plug in our 0, plus beta 1, 2 x1 times 0. Well, this whole term goes to 0, and this whole term goes to 0, because multiplying anything by 0 gives us 0. So I end up with just my original linear model again. So we get mu equals alpha plus beta 1 x1. This is why whenever we, like the level of our indicator variable that gets all zeros, or the level of our categorical variable that gets all zeros, that's why this is the reference group. Because now I just have a baseline model against which everything else is being compared. So beta 2 tells me how different my intercept is when I have a garage versus when there is no garage. Beta 1, 2 tells me how different the slope is when there is a garage versus when there is no garage. So let's interpret this. Alpha is the true mean price for homes when all predictors equal 0. So that would be size equals 0 and there are no garages. There is no garage. And we can see that down here in the second model. Alpha is the predicted average price, or the true mean price for homes for a house that does not have a garage, and when x1 equals 0, because there is no x2 to set equal 0 when x2 equals 0. So it's just that baseline group. Beta 1 is the true mean change in price for homes for a 1 unit increase in size. Well, where do we see beta 1? We see beta 1 alone when there is no x2 in the model. When there is no garage. So that is when x2 equals 0. So that is how x2 equals 0. That is how when there is no garage, this is our reference group. So again, whatever category has all zeros, that makes it our reference group. So with that in mind, we can now get beta 2. Beta 2 is the true mean change in price for homes with a garage. So it's the true mean change for homes with a garage versus those without a garage of a, for homes of a fixed size. And then finally, this beta 1, 2, as we've just seen, beta 1, 2 tells us, well here, this is the slope on x1, beta 1 is the slope on x1, but only when x2 equals 0, so only for homes without a garage. Beta 1 plus beta 1, 2, up here in the second model, this is the total slope. So beta 1, 2 tells me how different that slope is, how much more steep or how much less steep. So really, the change in the true slope for homes with a garage versus homes without. So it's the true change in slope between price and size for homes with a garage versus those without. So if homes with a garage have a steeper slope than homes without a garage, like we see here, then beta 2 will be positive because we're adding more to the slope. If, however, homes with a garage have a less steep slope, then beta 2 would be negative, and so because we would have to add less, we'd have to pull down that slope, make it shallower. So let's look at the results. Okay, so we have our prediction equation would be y equals a plus b1x1 plus b2x2 plus b12x1x2. So this is our interaction term again. So our interaction effect, and then our interaction term. So from here we have our whole model. So we've got A, B1, B2, and B12. So our prediction equation altogether would be, with some rounding, 141.83 plus 0.04 x1 for house size minus 120.4 x2 for garage plus 0.06 x1 x2 for the interaction. Does it make sense that this term is negative? That this intercept B2 is negative? Looking at the slope, or looking at the plot, it does, because the red line has a lower intercept than the blue line. Yep, so the red line is going to cross the y-axis lower than the blue line, and that's because the two lines intersect somewhere in the plot. This does not mean that the red line is always going to be lower than the blue line, right? So it no longer has that constant lower average for homes with a garage than homes without a garage anymore, because we have this interaction term. This interaction term, this interaction effect, means that on average we can expect a higher slope for homes with a garage than homes without a garage, and that slope is steeper by 0.06. So let's see how that works out. So when x2 equals 1, so there is a garage, we get y hat equals 141.83 plus 0.04 x1 minus 120.4, that's times 1, plus 0.06 x1. So if we lump all these terms together, we will get 21.43 for our intercept, and that's again just the intercept when there is a garage, plus 0.1 x1, and this is again just the slope when there is a garage. So this is intercept when there is a garage, and this is the slope when there is a garage. We can do the same thing when there is no garage. So x2 equals 0, no garage. And this is a little bit simpler to get because we just plug in 0 for x2. So we get y hat equals 141.83 plus 0.04 x1 minus 120.4 times 0 plus 0.06 times 0. And so we can see, let's compare these two things. The difference between this slope and this slope is that 0.06. So there is a slope when there is a garage that is 0.06 steeper, units steeper, when there is a garage than when there isn't. Similarly, when we compare the intercept when there is a garage and when there isn't, when there is a garage, the intercept is 120 units lower than when there is not a garage. Okay? So that's what these including this interaction term does. It's going to change the intercept, or it may change the intercept for the two things, depending on whether we have an intersection or not, and it will change the slope. So it's the change in the slope that that interaction term does. Now, how did I actually fit this model? Well, I created this interaction term manually in JUMP, and I created and fit that. So you can have software fit interaction terms for you, but it can sometimes do weird things like recenter variables and stuff like that. But humans are smarter. It makes things easier to interpret when we create our own interaction terms. So I will show you where I got these using my own interaction term. So here in JUMP, I've created my interaction term, and we can see that it's just called interaction. The three variables that we're dealing with are the house price in thousands of dollars, the house size, and the garage. And this is already an indicator variable. We can see that we have ones wherever homes have a garage and zeros wherever homes don't have a garage. Something that's very important to note is when you have an indicator variable, if we look at the column properties, or actually the column info, it must be numeric and continuous. So the data type for indicator variables must be numeric and the modeling type must be continuous. So remember, when we're including categorical data into our model, when we create indicator variables, we're doing that so that we have numeric data, we have continuous data, right? So we cannot include categorical data in a model, so if we were to make this ones and zeros and leave it as categorical, we would have problems. So the goal is to create continuous data so we can talk about an increase from level 0 to level 1 so that we have that 1 unit increase. So make sure that your data are numeric and continuous when you create an indicator variable. All right? So I created this interaction term, and if we remember what we had done in the notes, this interaction term is literally just x1 times x2. So I've got this x1 times x2 term in my model and in my prediction equation. And so in my data set, this interaction term is also literally just house size times garage. So we can see here I have a house size of 1,679 square feet. It has a garage. So my interaction term is at 1,679 times 1. And so again, if I had this as categorical data, I would not be able to create this interaction term because I can't multiply by categories, but I can multiply by numbers. Down here, I have a home that does not have a garage, so home number 12 has a house size of 2,755 square feet. It does not have a garage, so that 2,755 multiplied by 0 gives me 0. Again, this has to be numeric data, otherwise I can't multiply, and it just doesn't work. Now I've got everything I need to fit a regression model that has an indicator variable that has a quantitative predictor and that has an interaction term. And because this is now just a multiple regression model, I'm going to use analyze fit model. So my response is house price in thousands, and I'm going to include all of my variables of interest. So house size, whether it has a garage, and this interaction term, and they all go in my model effects. I want to understand the simple effect of house size, the simple effect of garage, and that interaction effect. And then I just hit run. And we can see here, so collapsing some of this output to get everything that I'm interested on the screen, we can see here that including all three of those terms, the two main effects, the two simple effects, and the interaction effect, explains 63% of the total variability. The overall model is significant, so I interpret the analysis of variance the same way. And then looking at the parameter estimates, I can see that, yes, holding garage constant, for any fixed level of garage, I do have an effect of house size. So as house size increases by 1 unit, for a fixed effect, for a fixed level, or really when garage is at 0 for homes with 0 level, or homes with no garage, I do have a significant effect of house size. This t-test is significant. I also see that I have a significant effect of garage. So there is on average a difference between homes that have a garage and homes that do not. And again, this is really just testing, do I have a difference in the intercepts now? All right, so really what's mostly interesting now is testing this higher order effect, this interaction, where I'm looking at both house size and garage at the same time, that difference of slopes. So this is saying, yes, I have sufficient evidence to indicate that the effect of house size on the sales price is not constant, that I have a higher slope, a steeper slope, because this is positive. So I interpret this as saying I have a steeper slope, a slope that is 0.06 units bigger for homes with a garage, because that's my indicator. I'm indicating for a garage, than homes without a garage. Overall, yes, this is telling me I have a significant effect, interaction effect. It's not telling me that it's significantly positive or significantly negative, because it is still a two-tailed test. So if we go back here, I have the same results here. So these are all two-tailed tests. So these are all testing the same thing. So this is testing beta 1 equal to 0 versus not, beta 2 equals 0 versus not, beta 1, 2 equals 0 versus not. So these are all two-tailed tests. And that's how we investigate interaction. So we had visual evidence of interaction because our two slopes were very different from parallel. I would prefer to use a prediction equation like this than that based on these results. I do not have evidence that I have parallel lines, and that's what that interaction is telling me.